Welcome back, Geos406 students. Today you're going to be doing a module that involves estimating the eruptive volume of the 2008 eruption from Okmok Volcano, Alaska. You're going to use one of the very standard tools in physical volcanology for estimating the total eruptive volume, which can help you estimate the eruption magnitude, particularly if you have some information about what the plume height was. So with this module, you're going to be using an exponential thinning model of a pile, and you're going to estimate tephra fallout volume, and then you're going to do a simple isopleth map exercise that'll allow you to estimate column height. From that information, you're going to be able to estimate the VEI scale of this eruption and recent eruption from an Alaskan volcano. All right, so we talked a little bit about what tephra fallout is. We're going to do some review here. Tephra is all particles that come out of a volcano during an explosive eruption. So that's very fine-sized ash, that's medium-sized lapilli, that's big blocks and bombs, and it doesn't matter what size or shape they are or composition. It's just a term that describes all clasts that travel through the air or are carried by the wind and eventually land on the ground. So tephra fall deposits mantle terrain, and they are deposited downwind from the volcano. They thin downwind because of the terminal velocity sorting from the eruption cloud, and they will thin exponentially with distance away from the volcano in a very basic sense. So here's an example from the May 18, 1980 eruption of Mount St. Helens. You can see on this ISOPAC map, we have Portland, Oregon. To the northeast is Mount St. Helens. When Mount St. Helens erupted in 1980, it produced a very large Plinian explosive eruption column. It went up very high into the atmosphere. The winds were traveling from west to east, as you can see in this ISOPAC map. And you can see that close to the volcano on this map, 300 kilometers in scale is noted down here. We had the thickest deposits, and they were of the largest fragment size. And then as you get further and further away from the volcano, these isopacs give tephra fallout thicknesses 2 centimeters, 1.5, and so on. Deposits from this eruption stretched across the northern part of Idaho and well into Montana. So isopac maps contour the thickness of the deposit. If you could kind of cut a slice through the axis of an isopac map and peel it away, you would get a sort of a thinning curve that looks something like this. In this graph, you have thickness in centimeters on the y-axis, distance in kilometers on the x-axis. And for the May 18th, 1980, Mount St. Helens ash, you can see this red curve. It thins away from the volcano. There's a secondary hump here. That's a little bit of a complication that sometimes happens, but you're not going to have to worry about that for this, this homework assignment. If we look at the YN layer of Mount St. Helens from 3,300 to 4,000 years ago, this green curve, that behaves a lot more typically. You can see that it thins away from the event in an exponential pattern as a function of distance. So there are several methods for measuring the volume of tephra fall deposits. One simple method is you go out into the field, you estimate or measure the thickness of the deposits from that one layer in as many locations as you can to great distances away from the volcano if you can. And then you make an isopac map of all of the different thickness contours as a function of distance. And then you can just take the areas of each isopac and then simply calculate volume. But this method is actually not accurate. It underestimates the volume because it doesn't account for very, very widely dispersed tephra. So a much better method uses some information about the eruptive process, and it assumes that, as shown in this graph on the left, the deposits thin exponentially with distance from the volcano. So you can use this this observation of exponential thinning to come up with a better estimate of volume, and you can interpolate better between the areas of observations where you might have observations that are missing. So places you couldn't measure, very far distances away. You can fill in the gaps with this exponential model. So that's what we're going to do with this homework assignment. Nowadays, we have much more sophisticated computer programming and models that can basically model the eruption itself. They can come up with very accurate thickness simulations from numerical modeling. And it's really highly effective and much more accurate, but it's actually really computationally expensive, and the math and coding are beyond the scope of this class. So we're going to use a very classic way that you can estimate volume from isopachs that is actually not terribly inaccurate, and it's something that you all can do and learn. Okay, so why do we care? So here's a VEI scale chart from Lockwood and Hazlitt. You can learn more about the VEI scale from the Smithsonian Institution volcano website down here. So VEI scale is kind of like the earthquake Richter magnitude scale. It allows us to estimate the magnitude of an eruption, how explosive it is, based on a few parameters. And then it can allow us to classify different eruptions throughout geologic time based upon geologic observations and compare with what happens today. It's a really great tool. It's actually used in forecasting models. So you're going to learn how to figure out the VEI number for the Okmok 2008 eruption in this homework set from the isopach and isopleth mapping exercise that you'll do. So VEI scales with size. So a VEI 0 eruption is non-explosive. That means really no tephra erupted. There's really not much of an ash cloud. It might have been a tiny little ash poof. It's just confined right over to the vent. This would be kind of like Hawaiian lava fountaining. Duration could be short. Lava flows are produced. There might be a lava dome. There's really no ash injection into the troposphere, and there's no ash injection into the stratosphere. As we go up in the scale, 1 to 2 to 3, we get into small, moderate, and moderate to large explosive eruptions. If we get to VEI scale 4, this would be a large eruption. The volume of tephra erupted would be between 10 to the 8th and 10 to the 9th cubic meters. The ash cloud column height would be about 10 to 25 kilometers above the crater. A qualitative description might be cataclysmic, severe. The eruption type is most likely going to be into the Plinian category or even Vulcanian. Some highly energetic Vulcanian eruptions can be VEI 4. The duration is going to tend to be long-lived, and you can have pyroclastic flows form, you can have substantial tropospheric injection, and stratospheric injection of ash is going to be happening. It goes on up from there. The very highest in the VEI scale of observed eruptions is a VEI 8. That would be Yellowstone caldera. In this case, you've ejected more than 10 to the 12th cubic meters of tephra. Your cloud column height is well above 25 kilometers. It's a colossal eruption. It's going to be loosely classified as ultra-Plinian, so super duper Plinian. The duration is going to be very long-lived, greater than 12 hours. You're going to have lots of pyroclastic density currents, and you're going to have lots of ash, both in the troposphere and in the stratosphere. These eruptions are very, very rare. So arguably Yellowstone approached a VEI 8. There have only been 4 VEI 7s recognized. And then you can see as we go on down the line, the most common size of explosive eruption is a VEI 2. This is actually not a terribly catastrophic eruption. Usually the hazards from a VEI 2 are pretty localized. This is the goal. This is what you're aiming for, is to use your results from this homework assignment to help classify Okmok 2008. So let's talk about Okmok. Okmok is a shield volcano. It's located in the eastern central Aleutian Islands. On Umnak Island, it's the next island west from Unalaska, which is where Dutch Harbor, the very productive fishing port in the United States, is. So Okmok typically produces lava flow eruptions of basaltic andesite, but occasionally it'll have an extremely violent eruption. It's produced Plinian, subplinian, violent strombolian, phreatomagmatic, and lava flow eruptions. It's done just about everything. The most recent eruption from Okmok occurred in 2008, and it lasted for 5 weeks. It was completely explosive. It produced a lot of ash. It did not produce any lava. So during that 5-week period, it caused evacuations of the cattle ranch, closures of the black cod fishery in the Bering Sea, rerouting of international air traffic, and isolation of Nikolsky village for over a month. So ash fell on Dutch Harbor in 2 occasions during this eruption. So it was actually an impactful eruption. So this photo in the lower left is one that I took from the cattle ranch during that eruption. You can see the ash cloud cranking out over the caldera, putting ash down over the Nikolsky village area to the southwest. Here's an image that shows inside of Okmok caldera before the 2008 eruption. You can see it's a big collapsed caldera, 10 kilometers in diameter. Inside the caldera are smaller cones that have grown up since the past 2,000 years when that caldera formed. All right, so right after that eruption in 2008, just a couple weeks after, I went out with my USGS AVO colleagues and we constructed an isopack map because we wanted to know the magnitude of this eruption, we wanted to know the total volume erupted, and we wanted to get an idea of what was erupted, what mechanism this eruption had, what its VEI number was. So here's some photos of us constructing isopack map. You can see in this photo on the lower left, it was actually really cold and terrible weather out there. It was kind of a grueling trip. We flew around in a helicopter to as many locations as we could. We'd jump out, we would measure the thickness of the deposit, we would collect area samples and samples for geochemistry. So how you do this is the upper left, you can see Joel Unema. He was a Northern Arizona University student at the time. He dug a pit through the ash, which is this brown muddy looking stuff, got out his scale and measured total thickness of the deposit. Here's a cross section of what that might look like on the right. Here's a thinner deposit section. You can see down here there's a little bit of grass and tundra and soil underneath this ash and lapilli fall. And so the mouse cursor right here is showing what the ash deposits look like. Here's the scale showing you that these are really thin. This was about a centimeter thick ash deposit right here. And then here I am again doing the same thing with a shovel, scraping away down to the soil, measuring the total thickness of the deposit. And then here in the lower right is me digging a big, trying to clean off this tephra cliff here that formed very close to the vent. So this is a really thick deposit of these ash layers close to the vent. You can see it's very, very thick here, whereas, several meters thick, whereas out here in the upper right, where we were about 10 kilometers away from the vent, the deposits are much thinner. So this shows you this exponential thinning as an example. All right, so the problem you're going to solve is what the approximate volume of the tephra deposits from the 2008 eruption of Okmok were. So you need data, and unfortunately we can't do this out in the field, but I'm going to explain to you how that works again, and I'm going to give you the data. So we dig pits, we look for natural or stream or man-made road cuts, and we identify the deposit we want to measure the thickness of. We measure the thicknesses of those deposits. We also collect a lot more observational data and samples to get the chemistry and the componentry of the deposit. Then you have a map base. In this case, I'm showing you an example of what my isopack map looked like from this eruption. You can actually use this to get an idea of how close you are to where you draw your isopack lines if you want. You can see all the little red dots. This is Umnak Island. Okmok caldera is right here. It's this big collapsed caldera in the center of the northeastern part of the island. And all of the little red diamond symbols here are locations where we stopped to measure deposit thickness. You can see that deposit thicknesses range from over 1,500 centimeters near the vent, which was right around here by this big cone that I'm circling. And they thin all the way out on this northeastern coastline to 7.6 centimeters. Down here, they're as thin as 2 centimeters on this coastline. And then way down here, they were very, very thin, 0.2 centimeters right here. So that's 2 millimeters thick, way down here to the southwest. So you're going to have all of these, you're going to have a simplified version of this map with thickness information given on it, and you're going to draw the isopack contours around it using the ImageJ image processing program. Okay, so just to repeat, for this lab, in your Blackboard course materials area, I give you a copy of this digital elevation model, and I'm going to give you thickness information for different locations around the volcano. And you're going to be asked to draw the isopack contours around those deposit outcrop thicknesses that you're given using ImageJ. You can draw right on your digital picture in the ImageJ program. So you're going to be given the map that you're going to upload into ImageJ to do this in Blackboard. So you'll then use ImageJ to calculate the areas of the isopacks. This is pretty great. The program will do it for you. It's a little more accurate than drawing it yourself and then estimating using a ruler. So then you're going to take the thickness versus area information for your isopacks to apply to the exponential thinning model to figure out what the eruptive volume of this eruption was. For the second part of this module, you're going to estimate simple isopleth contours of approximately equal class size. So I'm going to give you a second map that shows different class sizes as a function of distance from one of the phases of this eruption, just the initial phase where the plume height was the greatest. So you'll take that isopleth data and you're going to estimate plume height using the model of Carrier and Sparks. Together, the volume and plume height will be used qualitatively and semi-quantitatively to assess the dynamics and intensity of this eruption. You're basically going to come up with the VEI number and an estimate of what the eruption style was. So on the lower left here, this is an example of what some of these eruptive products from this volcano look like. So this location 13B is way out here along the northeastern coast. You can see these clasts here. They're actually juvenile magma. They're little scorias, and they're basaltic andesite in composition. These are all about 2 to 3 centimeters in size. Okay, so you're giving the map image file from Okmok in your Blackboard course materials folder, and it has the thickness measurements from the different locations around the volcano. You're going to be using an image processing program called ImageJ. It's totally free, and it's actually a really great program. So follow the instructions in the ImageJ instructions file in Blackboard to download and start using ImageJ for your map image. I also give you instructions for how to set the scale so that you're reading your areas in ImageJ in kilometers squared. And you're going to want to use the set measurements menu option to set the measurements to automatically estimate areas from your drawn isopacks. So in ImageJ, you're going to use the polygon tool to draw the isopacks as more or less smooth curved contours around each of the thickness contours that are specified here. So the thickness contours you're going to draw are 1,000 centimeters, 500 centimeters, 100, 50, 30, and so on, down to 1 centimeter. There are going to be locations where you're going to have to estimate and interpolate your isopacks because you'll see not all of the measurements fall evenly at these ideal desired thickness contour intervals. So when you set the measurements in ImageJ, the program will automatically determine the areas for you. Be sure to set the scale in ImageJ to convert pixels to kilometers. You're given a scale bar on your map, so you can use this to estimate how many pixels in the image represent kilometers on the real world scale of the volcano. You want your areas to be in square kilometers, not square pixels. That'll goof up your calculations. And you'll note your thicknesses are in centimeters. We don't measure thicknesses in kilometers out in the field because it's, well, you can imagine it's a lot easier to measure it in centimeters. So you're going to also have to convert your thicknesses for your isopacks into kilometers in order to make your calculations internally consistent and give you the right numbers. Okay, so we're going to do an exponential thinning model, and I'll get into that in the following slides. You're going to plot the natural log of thickness as a function of the square root of the isopack area in place of distance from the volcano. And this will help average out the effects of the wind. you're going to use the Excel trendline function to fit a line to the natural log of thickness versus square root of area data to estimate the parameters of the exponential thinning model of pile. So with these parameters in hand, you can actually pretty simply get a volume estimate for your deposit. So here are the equations from pile. This is an exponential thinning model that Pile published in 1989, and it helps estimate volume more accurately than if you were to just add up pancake stacks of isopachs in your map. So in the exponential thinning model, deposit thickness, capital T, depends on area of the deposit, capital A, and it has a thickness greater than T. Your initial thickness at the vent, T sub 0, and you need a thinning constant, little k, to help provide the right rate of decay of thinning for your deposits as observed from the map. So the equation you're going to start with is T equals T naught e to the minus k a to the 1/2 of the square root of area. The equivalent half thickness is basically a decay constant. It describes how this exponential decay curve progresses from close to the vent to far away to accurately describe the actual deposits that you observe. So the half thickness is the average distance from the vent at which the deposit reaches 1/2 of its initial thickness. So it's basically the half-life of exponential thinning of your deposit. It's a measure of dispersion of the deposit. So B sub t is equal to natural log of 2 divided by k, which is the same k as up here, times the square root of pi. You can then rearrange these terms and do some math that I'm not showing here, but is in your background slide coming up. The volume of the deposit can be estimated using the parameters T naught, your initial thickness, and the decay constant B sub t as follows. Volume equals 13.08 T sub 0 times BT squared. Okay, so you're going to use the information from image J and the isopach map to calculate volume. In this case, you're going to take your estimated areas enclosed by each isopach based on the deposit thicknesses. So you'll get the areas from your contours you drew in image J. The program will calculate area for you. You're going to want to enter those data into your spreadsheet. I have a spreadsheet template in the Blackboard course materials area that looks like this. And you're going to want to set your spreadsheet up, either your Excel spreadsheet or Google Sheets or whatever spreadsheet program you're using, to look like this. I've given you isopach thickness in centimeters. You're going to convert those to kilometers. You're going to enter the isopach areas you measured from image J, and you're going in square kilometers. You're going to calculate square root of area and the natural log of thickness as your first steps. Be sure to set the scale in image J to convert the image pixel scale to kilometers using the map scale bar given to you on the map. You're going to want deposit thickness and isopach area in kilometers before plotting. If you plot deposit thickness in centimeters and isopach area in square kilometers, you're going to have a whole messed up situation that's not going to work. So just be sure to check your units. So you're going to plot the natural log of thickness as a function of the square root of area. Your plot's going to look something like this. This is an example that I have plotted from my own attempt at doing this homework problem. Note that the equation T equals T naught e to the minus k a to the 1/2 can be simplified as the natural log of t equals the natural log of t naught minus k times the square root of area. So you've just taken the natural log of everything right across the board on that exponential equation, and you've converted it into something you can plot that can be fit with a line. So this is now a linear equation. So the slope is little k, the intercept is ln t naught, and if you plot ln t versus the square root of area and fit a line to this, you can use the line equation y equals mx plus b to estimate little k and the intercept ln t naught. So when you fit your line, it's going to look something like this. You'll notice it's not a perfect line fit. but for this purposes, it's going to be good enough. So the parameters T naught and B sub T ultimately are estimated by fitting this linear equation to the data. So the equation of the line fit is y ln t equals intercept, or b ln t naught, minus k square root of a, which is the mx part of your equation. So select the options in your spreadsheet program or Excel to display the equation. It'll give you the y equals mxb form of your line fit, and you'll be able to extract ln t naught and k from that equation. You can then use the equations I gave you on a prior slide to start to estimate volume. So in this case, the half-life b sub t is equal to ln of 2 divided by k times the square root of pi. So b sub t, you know, is the, k is the slope of your line. It's given to you by the parameters that you extracted from your trend line fit. In Excel, this would be the trend line function. And you can rearrange this equation to calculate b sub t from k. When you have b sub t, you can put it into this volume equation here. Volume is equal to 13.08 t naught times bt squared. You've already obtained the ln of t naught here because that's the intercept to your line fit. So all you need to do is raise ln t, to an exponent to extract the t naught, and then you can calculate volume. All right, so in Excel, you can do a linear regression pretty easily, actually. Google Sheets, it should work just as well too, although some of the steps might be a little bit different. So you need to become familiar with how to do this, add a linear fit or a trend line to your data in whatever spreadsheet program you're using. In Excel, you want to use the worksheet, be on the worksheet which contains the chart you wish to work with. Move the mouse cursor and to any data point in your array of plotted data and press down on the mouse button. You just want to select all of the data points. So now you can go to the Add Trend Line from the menu up in Excel. You'll need to find it if you're on a PC. I know where it is on the Mac, but the buttons are a little rearranged. So from the Trend Line option window, click on the box of the line fit that you want, for example, linear. So select linear. For the options at the top of the trend line menu, you're going to want to display equation on chart and check the box next to display R squared value on chart. So don't click the text box that sets the intercept to 0 because you want to know what the intercept is for your ln t naught, and click OK. So when you do your trend line regression, you'll get a graph that pops up that looks something like this, where your equation is displayed here. That's y equals mx plus b. R squared is given here. So in this case, it would be ln t equals the minus 2.886, which is your k. X is square root of area. And your intercept, ln t naught, is 0.0221 in this case, in this example. So there's some background, and I'm not going to go through this, but I encourage you to read this slide. If you really want to get in depth, I'd be happy to get a copy of the pile paper for you. Okay, so in the next part, you're going to make simple isopleth contours for plume height. You're going to use the second image that I've given you. It's in the Blackboard course materials section. It's a second map, same as the isopack map, but now you're going to see different things on it. You're going to see locations labeled A, B, and C. These represent the distribution of different sizes of glass that fell out of the plume from the volcano during the 2008 eruption of Okmak. So locations marked C represent clasts that are on average 6 centimeters in size. Locations marked B are those that are on average 3 centimeters in size, and A is a 2 centimeter in size on average clast. You're going to use image J again to draw isopleth curves around each region enclosing class sizes A, B, and C on your map. You can measure the downwind range and half width by two methods in image J. Make sure you set the scale so that it is in kilometers like you did with the isopack map. You can fit ellipses to your contours and extract the major and minor axes. The major axis will give you an estimate of the downwind range, and the minor axis divided by 2 is the half width. Or you can just use a line measurement tool in ImageJ to measure the downwind range. So that would be from the apex of your contour all the way down to the maximum distance away from the vent. That would give you your downwind range. And then you can approximate the half width just by measuring half the distance across each isopleth contour at its widest point. So you're going to use this information with the model of Carey and Sparks to estimate the plume height from the downwind range and half width of your 3 isopleths. You're not going to employ the full mathematical model published by Carey and Sparks. Instead, you're going to use the graphs for each of those class sizes, and you're going to come up with 3 plume height estimates. You can take an average and get a standard deviation of error on that plume height estimate. And then you're going to compare the plume height estimates with an estimate published by me and co-authors in 2009 that were based on direct remote sensing observations during the eruption. So this is what we're talking about here. This is from Carey and Sparks 1986 and Sparks 1986. Here's an estimate of what an isopleth map looks like. This is for a wind velocity of 30 meters per second. The half width here is in kilometers from 0 to 5 and 0 to 5 in both directions. The vent is here. These are the extents of each isopleth lobe, 6.4 centimeters, 3.2, 1.6, and so on. The downwind range is measured from the vent or the apex of that isopleth curve to the maximum distance represented by that isopleth curve. The half width is estimated by taking the widest point in that isopleth curve and measuring halfway across its width. So you can see here of the 2 methods I suggested you could use in ImageJ, perhaps the direct line measurement estimate is the most accurate. If the isopleths are elongate away from a true ellipse, the ellipse fit method might actually underestimate the half width. All right, so you don't have to calculate. I'm just going to want you to take a look at these graphs, and you're going to estimate plume height from your downwind range versus isopleth half width for each of these class sizes, and I'm going to give you a wind speed to match. It's going to either be A or B, or the no wind case. So look for that in your homework Word document to know which of these curves to estimate. And then you're just going to take and plot your estimate on this graph. So say you have a maximum downwind distance of 15 kilometers, and you know your wind speed matches B, and your isopleth half width is about 7.5. So you know you're going to fall right around in here. And for the 6.4 diameter class, it's going to estimate a plume height slightly above 30 kilometers. So just do this eyeball method. Your samples are not going to exactly correlate to the model class sizes, but they're close. And just basically extract the information from the graphs, because I don't want you to have to code and recreate the whole model. That's beyond the scope of the class. All right, so here's your instructions. I know this PowerPoint was a little bit more lengthy and complicated, but really once you get into this module, I think you'll find that it goes pretty quickly and easily. So first, read the PowerPoint file completely, get all of the background information, write down the equations you need and all of the instructions. Then read the Word document homework assignment completely before getting started. Make sure you know what's expected of you in all parts of this assignment so you don't miss anything. Then read the instructions for how to use ImageJ completely before downloading that free program and using it to measure your isopack and isopleth contours. So your first step is going to be to download the Okmok DEM shaded relief map from Blackboard, and you're going to upload that into the ImageJ program so that you can annotate it and make your measurements using that program. So you'll draw the isopack contours around the deposit thicknesses in ImageJ. You're going to use the thicknesses that are given to you in your Word document and also in the example Excel spreadsheet. You're going to notice that the thicknesses don't always agree with the ones you're asked to draw around, because in real life field geology data, you're not going to end up measuring these isopack contours precisely around one number. You're going to basically get the observations you get from where you can go. So you might have to interpolate in between isopacks as needed. Then you're going to transfer your area and thickness results to a spreadsheet, and you can use the template I have given to you in Blackboard to set your spreadsheet up. You're going to perform the thinning model calculations for volume based on the formulations of Pyle. Then you're going to go on to do the isopleth mapping and measuring as above and compare with the Carrion Sparks model to estimate plume heights. Then you're going to have some questions to answer to place your model results in the context of the Accomac 2008 eruption. And as always, if you get stuck, please let me know as soon as you can so that I can help you. Thanks and good luck and have fun.